Hello, and welcome to our Intro to Machine Learning course. Today, we're going to be covering quite a bit. So first, we'll just kind of go over the topics that we'll be covering here. So first off, what is machine learning? Supervised versus unsupervised learning. So, labels, no labels, generalization, pre-processing. What is normalization versus standardization? Training of machine learning models. So train test splits, cross validation, and other kind of validation, model validation techniques, hyperparameter tuning, to get the most performance out of your model, the bias variance trade off, and then be ending on just your basic evaluation metrics or classification metrics and regression metrics. So you can figure out what is the best version of your machine learning model, or out of these models, which one is performing the best. So first off, what is machine learning? Well, just simply put, it's how a machine can learn. It's basically a family of statistical techniques that gives computer systems the ability to learn from data effectively, or in some cases, in some newer techniques, I guess not from no data, but from very little data, being able to learn how to perform a particular task. The whole idea is that you're programming with data and not explicitly programming with code. So, want to real quickly talk about some of the kind of differences between different terms that are kind of tangential to machine learning. So, at the broadest scope, we have AI, and this is a pretty solid definition. It's just saying artificial intelligence is computers that are at least trying to imitate human intellect and behavior. So you've played like a chess AI before. A chess AI can't cook, but it could beat you in chess, right? And then under that we have machine learning, which is statistical algorithms that enable AI implementation through data. So basically, whereas AI could be a bit more of a broad scope, like it could be like a really long series of complicated if statements that was at one point written by a human that is designed to imitate human level performance on some task. Machine learning is exclusively using data to learn how to do a task. And then there's another common term called deep learning. Deep learning is almost exclusively used to describe neural networks, which is probably one of the most, if I mean, right now is the most effective machine learning method out there. And that's kind of a subset under machine learning. Machine learning would contain tons of other algorithms as well, from simple linear regression, logistic regression, to something more complicated, like XGBoost or something like that, all the way up to max complexity, which is probably right now like large transformer models, or maybe some like neural based reinforcement learning models, recommendation systems, et cetera, et cetera. So deep learning is a subset within machine learning and only really typically describes neural networks. Machine learning is a family of statistical algorithms, and AI describes kind of really any program that's trying to mimic human behavior in some way. So this slide is just here to kind of convince you of the importance of learning the skill set. So here we have a graph of growing use of deep learning at Google. Here we're plotting deep learning, so only plotting the growth of use of neural nets over time at a company like Google. But really, the graph for machine learning would look very similar to this. Perhaps you would see it start to take off slightly earlier than deep learning, just because machine learning is a little bit more simple, and probably started seeing use a little bit more before the growth and kind of explosion of deep learning. But certainly neural nets are taking over right now, and you're seeing more and more machine learning kind of permeate daily life. So naturally, it's there's a lot of rewards given to those who can control and make these models. It's definitely the work of the future, and more of the work of the future is being done by machine learning. So really highlights the importance of being able to build these machines. So, what are some different common examples and use cases of machine learning systems? So, here we have statistical machine translations. Google Translate, translating one language into another. The data set for that would be having an English and non-English examples, or any one language converted to another. recognizing faces, so you put these bounding boxes around faces, and the model can learn to do that. We have a picture of friends here, and actually not even just recognizing that these are faces, but even labeling whose faces these are. So we actually have bounding boxes around the faces of where the faces are, but also who these people are with the names. Recommendation systems. So say like Netflix, or in this case, we have tweets. So based on the history of tweets that you have liked, let's recommend other people that you might want to follow, or friends that you might want to follow. Or if you're watching Netflix, based on your watch history, what other movies do you want to see? If you're on Amazon, based on the products that you've purchased, what else might you want to buy? Then semantic segmentation. So here we're kind of segmenting out different portions of an image. So you can do all kinds of things with machine learning. These are just some examples, but I promise you the opportunities are pretty much endless, and they only get bigger um, day by day. There's more and more things you can do with machine learning. The more data that gets produced, the more things you can do with ML systems, and data, as time goes on, is becoming even less of a constraint than it previously was. So here, just furthering the importance of learning the skill set, here we have a graph of companies in different industries along with their self-reported profit margins according to their different, whether or not they have adopted AI into their business strategy. So we have non-adopters, partial AI adopters, and then full AI adopters. And as you can see, the orange line is just, really pulling far and away from the other companies. So, this makes sense. The more you automate, typically the higher profit margins you can take out. You're more highly leveraged. It's kind of how I like to think of it. So you know this skill set pays. Imagine you can be the one in a financial services or even retail. And where Levi's is in retail, you have a profit margin going from potentially negative up to like positive 9-10%. And think about, like, what if you're the person that helped do that, and what kinds of things come your way if you're the person that can help drag an organization up to higher profitability using your skill set that you learned. That's why we're here today, and that's why it's important to learn this skills. So let's go over the machine learning workflow. This is something that I think has been subtly changing over time, but I think it's still good to kind of go over it as it's depicted here. So here we're looking specifically at a workflow for image data, which I think might actually be a little different than certain other kinds of data, and I'll talk about that a little bit more in a moment. So here we have the training phase. Let's start with that. This is the beginning of your journey. First would be getting images and labels. So actually, before that's even in this graph, the first step is making sure that you actually have a lot of labels and a lot of images. And you can actually tell whether or not you have enough labels and images by actually training a model and seeing how it performs. But I think you want to be, more than like a few hundred, ideally, at least to start, if you really want to hope to get something useful out of image data here. Ideally, much, much more. So the first step is actually gathering the data, which, not depicted here, but often can be a long and arduous process. Then you have this feature extractor here from the images. Now, back in the day, at least with images, this used to be a manual process. Nowadays, for images, this is typically a much more automatic process. Once you feed images typically into what is a very large neural net model, it'll kind of learn and figure out the features it needs in order to classify data for you. And other kinds of data workflows, this is becoming more common where it is kind of being automatically done by a neural net, but um, there are a lot of cases where you're still the one kind of cleaning up the data, engineering the features yourself for a model to better understand what's going on, and then feeding those features into a model and then getting out better performance as you kind of manually tune how the data gets fed in. But for the sake of images, this is typically automatic. So features go into the model, your machine learning algorithm, whichever you choose. In this case, I think I've alluded for images. Certainly the best choice would be a neural net for images. And then you have the prediction phase. So after you're done training and you validated that your model is running well, you're getting good performance out the perform, and you've kind of plotted out like what that performance looks like, and for you and your company in the real world, you would then deploy that model, and then that model will now be in the prediction phase. So you have to set up a pipeline to digest in new images that have not yet been seen in your training data set, that go through the same kind of process. So the features be extracted, features get put into the trained classifier now. Same thing as your machine learning algorithm, it's just a fitted model. And then you get the label output. So before you had to give all the labels to the model, and the images. But now you just put in an image and you get out the label for future data. And this is the typical use case for machine learning is you're trying to get it to predict things about things using lots of data. That's that this power. This is a very very powerful paradigm. This very simple little graphic we have here depicts like probably somewhere in the neighborhood of like 80 to 90% of all machine learning. So let's talk about some common groupings or different, like a distinction between two different groups of different kinds of machine learning algorithms. So let's first start with supervised learning versus unsupervised learning. So supervised learning, what you're doing is you're training a model to learn that given an input, output a certain label, and you already have the labels for the model to learn how to optimize for. So, for example, say you have a bunch of images of cats and dogs, and you're trying to label whether or not there's a cat or a dog in the picture or both. So you have these labels, and the model looks at the label and it says, okay, there's a cat and a dog somewhere in this picture, and I have this picture. And then the next picture it sees, okay, it says there's no cat or dog in this picture. Look at the picture. Okay, I'm starting to figure out the patterns, I think, for what determines whether or not there is a cat or a dog in this picture. So you're learning from examples. This is usually a much easier kind of learning. I mean, like even for humans, I think we do a lot better when we're learning from example. Whereas unsupervised learning, you have no labels, so you're trying to exploit like natural patterns in the data. So in the unsupervised case, it would just have pictures of cats and dogs, and then without any labels, you're trying to find the pattern that makes up a cat versus a dog and trying to like retrofit that on. Like that's a lot more difficult of a task. So often what you'll do is you'll have throw an unsupervised learning algorithm at your model, and you'll get out these like patterns, and you won't necessarily fully understand what it has found. It'll take quite a bit of diagnostics and kind of analysis to figure out like what is the model thinking, or like what has it really found. Whereas for supervised learning, this is a much easier task because it's a lot easier to kind of learn the relationship between the input and the output label, so you can get an idea of like how it went about making its decision, at least a lot more easily than in the unsupervised case. So then the second distinction we'll have here is continuous versus discrete. So continuous means you just have like a continuous number. So the case of like regression, for example, what you're doing is you're trying to predict, like say a number between 0 and 100. So the output, monotonically like increases or decreases, and you're trying to figure out the relationship between the inputs and your output, continuous variable. Whereas in the example of cats and dogs, our variable was discrete. It's either a cat or a dog or both, and it's not like, you can't plot cats and dogs on any kind of like linear spectrum or anything like that. Whereas, so then on the unsupervised case, dimensionality reduction, we're trying to reduce data down to uh, less features. That's another form of unsupervised learning. So we have a highly dimensional set of features, and we're trying to reduce it to little. Now, I'm saying, these words features, high dimensionality, low dimensionality. Basically, what I mean is we're trying to explain more with less. Is effectively what dimensionality reduction is going. We'll get more familiar with the kind of different terms I was just using in the next few slides. So building on the last slide, let's kind of go a little bit more in detail on those different use cases. So supervised learning, classification. So we already kind of alluded to this with our previous example of labeling cats and dogs. But basically classification is the problem of identifying which category or set of categories does a particular data point belong to. So again, in the images, you either have a cat, dog, or both. And you could have way more classes or way fewer classes that you are trying to label. Classes and label mean the same thing. So we're just trying to classify whether or not, or it doesn't have to be whether, it doesn't have to be binary. You, you can just classify which classes a particular data point belongs to. That is the process of classification. So unsupervised learning clustering. So clustering is the process of using patterns in the data to automatically group your data into groups. So here we have a two-dimensional graph. So two dimensions meaning, so we have two axes. So we're plotting points on the XY plane. And if you take away, pretend you didn't see these colors here, you would probably still be able to distinguish that there are three rough groups of data points here. So clustering works really well in situations like this where, especially in the case where you're using like a distance-based clustering, it tends to kind of often fall into these sort of clouds, these central that has like a centroid and points that kind of sputter about it, that you can easily put into a singular group. So what clustering will do is it uses some algorithm to find a way to find the best groupings of data points. This doesn't always work well, depending on how your data is distributed, and clustering can really vary in performance depending on kind of how your data is formatted, or even just like what kind of patterns exist in the data. So, unsupervised learning, it can be really great, but it can also be a serious challenge, again, because you don't really have an output that you are necessarily exactly looking for. You're just hoping that it finds good patterns in your data, and it's up to you to validate whether those patterns make sense or not. So let's talk about this concept of generalization. So we have a definition here. It's the ability for an algorithm to predict output data for data which has not been used in training. I think there's a kind of a more abstract definition to be had here. It's basically like how well the model stores features, like how condensed it's able to store high quality features to predict new outputs. So, a model at some point has to make a more condensed representation for whatever it is that it's trying to learn, to then output something else. Like, you could have a model that just memorizes all the cases, but you wouldn't say it's generalizing in that case. You would just say, oh, well, you just memorized all of the input data and gave me the correct output data. So that's why this particular definition is talking about predicting for data which it hasn't seen before. But I would actually go beyond that and say how well it's actually storing representations for learning patterns within the data. The better you generalize, the more you could say that the model understands, or the more like the model has been able to store like high quality signal for whatever it is that it's being trying to predict. So underfitting versus overfitting. Underfitting is when a model usually doesn't have enough data, or just doesn't has too few parameters or not enough data in order to describe the data well, which leads to large model bias and just underperformance of what it could possibly be. Underfitting is less often the problem compared to this next one, which is overfitting. Overfitting is when the model has too many parameters for the data that it's trying to learn. So it's not necessarily too many parameters as much as the model is not actually generalizing, as we were talking about in the last slide, which is so if the model doesn't learn a generalization of the data and it's outputting predictions and it might be getting things correct, it's most likely memorizing the answers and not actually generalizing well. I mean, overfitting is a problem because when you try to throw new data at the model, it often performs horribly, whereas it does really well on the training data because it's memorized examples. But then you have anything that looks different than the training examples that it's already received, and it doesn't perform well. Yeah. So, on other fundamental machine learning concepts, data normalization. So, the most common definition of data normalization, when people say normalization, one that you'll find in more technical textbooks, is this one, which is a normalization is a scaling technique in which values are shifted and rescaled so they end up being between 0 and 1. And the most common is shown in this equation, which is you take the data minus the minimum of that data distribution divided by the max minus the min. um, this is one way to do normalization. There are other ways as well, as far as like getting values between 0 and 1. But data normalization can also mean beyond putting values between 0 and 1. For example, there's this idea of text normalization, which is trying to get as few tokens to represent as few semantic concepts. Basically, the goal of normalization is to make data more comparable, and to have as close of a relationship of like one-to-one relationship between data and concept is how I would kind of describe it. You want your signal to be very clean and easily interpretable by a model. And that's why we normalize. If you had a feature that is ranging between like 0 and 100,000 versus the one that's 0 and 1, sometimes it's a little harder to detect magnitudes of differences and relationships between those two features than if they were both scaled between 0 and 1. It's just easier for a model to play with this, and learn from data that is typically that is the case when data is normalized. So another common thing to do to prepare your data for input into a machine learning model is standardization. Standardization is really similar to normalization, except instead of scaling your data between 0 and 1, what it does is it makes the mean of your data be 0 and have a standard deviation of 1. What this does is for certain models that make assumptions about your data being normally distributed, this is a really effective way of doing that, such that it'll scale your data and it will satisfy your model's assumptions. And the way that you do this is you subtract the mean from your data point and then divide by the standard deviation. So another really important idea in machine learning is this idea of train test split. So what this means is you have a training set separated from your test set. So you will train on the training set and then you reserve part of your data set to test on to make sure that you are performing well on data points that you have not yet seen. So you don't really measure the training error, we measure the test error to know how our model is doing. So validation set and cross validation. First, let's talk about what a validation set is. This is a really confusing concept, I'd say, for beginners, and I was for a long time had a wrong idea on actually what a validation set it was. So you have your training set and test set. So I think that much makes sense. You train your data and then you hold out some data in order to test on it. But it's also common to hold out what we call a validation set. And the reason we do this is basically to prevent you, the researcher or practitioner, from messing up. So it's very common when training a model to train your data and then you will test that data using your test set, right? But then it's common for you to tune what you call your hyperparameters. So these little parameters on your model that kind of change the behavior of the model. And then you'll change those parameters over time in order to perform better on your test set. The problem with this is that you can become vastly overfit on your data depending on how you tune these hyperparameters in order to perform well on the test set. This is why we also have a validation set. That way, when you're tuning your hyperparameters, you are testing on the validation set, and then you have another holdout test set in order to make sure that once you're done tuning your hyperparameters, that you actually are in fact performing well still on the test set. Okay, I think that makes enough sense. It's like, you have your automatic training, and then you kind of have this iterative training that you, the practitioner, are doing, and you test that with a validation set, separate from another test set. So you still have an unbiased test on how well your model is doing, and how well your hyperparameter selection is doing, without optimizing towards this particular test set. So you'll still have an unbiased estimation of how well your model is doing, even after you've kind of potentially risk overfitting using your hyperparameter tuning on the validation set. So then we have something called cross validation, which is a much more effective way of testing how well your model is doing. So what cross validation does is it kind of just moves what these validation and test sets onto different segments of the data. So what you'll do is you'll kind of randomize your data, segment it up, and then you will move which sets are the tests and training sets and the validation sets, and train your model on all of the different segments of variations of training sets, and then validate and test on the different validation and test sets. That way, like when you're training your model using cross validation, you kind of see different segments of data and validate that the model is still performing on different test sets that are being held out. That way, you're for sure that your model is not overfit. Cross validation has some other uses as well. What you can do is you can do what's called a learning curve, which is you plot out like how many data points your model has seen thus far. So you'll plot out your model trained on like 10 data points, and then 100 data points, and then 1,000 data points, and you'll plot out your cross-validated error, and then you'll also plot the training error. And what you'll see is on the top, you'll see a training error that starts very high because it's overfit, and then it starts to converge closer and closer to the cross-validated error line over time. And what this allows you to do is it allows you to know how many more data points you need until your model is what we call converge, which means the two lines, the training error and the cross-validated error, are getting closer and closer over time. If you Google learning curve, you'll be able to see what I mean. So this is what I was referring to earlier by hyperparameter tuning, is basically you have these different parameters for different models that kind of change the behavior of the model. And different configurations of these parameters can greatly increase or decrease the accuracy of your model. And see, you can see here the 10-volt cross-validated accuracy be like 90%, 80%, or 90%, 95%, according to different hyperparameter configurations. And this is why, again, we have a validation set, because like you, the practitioner, are enacting a level of skill to optimize towards a certain data set. So it's very possible that you're getting 90% validation error, or 95% accuracy on a validation set, but then you go off and put it on the real world, and suddenly it looks like your model is overfit. That's why you have an extra test set to make sure that, in fact, you aren't actually overfit to your data. So the next concept we're going to be talking about is bias. So, and this is statistical bias, which has some relations to like real world bias, but here it's not necessarily the same thing. It's a common misconception. So let's talk about like this the statistical definition of bias. Bias is the difference between the average prediction of our model and the correct value, which we are trying to predict. So another way to say it would be like bias is like kind of when an algorithm has limited flexibility to learn the true signal from the data set. So models that end up with high bias are typically underfit, meaning they're like learning overly simplistic um, representations of the data and aren't using all of the information in the data in order to make a prediction. So see, we have these lines here, but we have this kind of curved data set, right? So we're using a linear regression, which a linear regression, it can only learn models in terms of a line. But you can see here, we have this kind of curved data set. So a better model to fit this kind of data would be a model that can learn a representation that can have this kind of curved attribute. So a model that could draw a curved line, right? Whereas a linear regression can't really learn a good representation for this data. So naturally, it has high bias because it doesn't actually have, it can't use all of the information that is actually available in the data set. So that's what high bias indicates. And the reason that you can think of this intuitively is because it's the average prediction of our model and how far away that is from the correct value, right? So because it's like the average prediction, if we notice that this average prediction is often more and more wrong, it indicates that we aren't using all the data and we aren't learning good representations, and often might even indicate that you might just want to use another model entirely or change your hyperparameters or something, or rather. On the other side of the spectrum of bias is variance. So variance is the variability of a model's prediction. So we have the same graphs as we did before, but we're plotting um, lines that are much more sensitive to the data, and that's kind of how I would describe the variance of a model's prediction. Is generally it indicates like how much it's closely following the lines, as you can see here, kind of on the far right of our graph here. Like it kind of shoots up and down in order to shoot through as many data points as possible. This kind of has the opposite problem, whereas a model with high bias hasn't learned a good representation in that isn't using enough of the data. Variance is overfitting to each individual data point, and this is kind of what I would describe as, like earlier I was saying the model just memorizes the data points. This is kind of what I meant by that, is that it is fitting to every possible data point that it can, and therefore is sort of memorizing the data rather than learning a more solid generalized model that would perform better for new data points. So it performs really well in the training data, a model with high variance, but it does not generalize well to new data. So we would call that model overfit. So here is a visualization of kind of low variance, high bias, and low bias, and what these kind of look like together. So in this example, we have a model that's trying to learn to shoot a bullseye, a fairly simple task in this like two-dimensional space, assuming that the model is sent to learn how to use an arm and such. Anywho, so here over on the left, we have low variance and low bias. You can see that the points are very tightly coupled together, and it's like almost dead center on the bullseye here. Whereas if we go to high bias, we can see that the data are that our predictions go up vertically quite a bit because the model is biased in the y direction positively, right? So it's and positively, like numerically, not positively isn't a good thing. It's missing the bullseye. Whereas high variance, we see this kind of scattered um, data points about the bullseye here, but it's missing. But you can see that it's varying around the center. Whereas bias, high variance, you see points that are much more scattered, but they are also much more vertically oriented in the positive direction, away from the bullseye. So that's the worst performing model. So here we have the classical bias variance trade-off. You'll see this in a lot of older machine learning textbooks, even modern ones. But there is a chance that this doesn't hold as true for some certain kinds of modern models, which I'll touch on a little bit. But first, let's understand what this is. Walk before we can run. So here we have three lines. We have our variance line, we have our bias line, and we have our optimal complexity. And our axes are error and basically like how complicated, how complex the model is here. So um, basically what we want is a model that is complex enough such that the model doesn't have too high of bias. So the model, like performs well, it captures, like, it can use all of the data available to create good generalizations. However, the model should be also simple enough such that it doesn't overfit or overgeneralize. And this graph here holds true for pretty much all classical machine learning models. So linear regression, logistic regression, random forests, naive Bayes, anything you would find in the scikit-learn library. However, there may be a kind of a secondary story for this graph when it comes to neural nets, which is kind of a good thing to keep in mind. It seems that with neural nets, the more parameters we add, actually, we don't necessarily overfit as we would traditionally expect on this graph. This certainly is the case with linear regression or some other more complicated regression with more parameters. However, with neural nets, it seems that it's able to learn complicated relationships, um, and without, even if your model is way over parameterized, it's still not overfitting. An example of this would be GPT-3, which is 130 billion parameters. Granted, it's scraped and tried to learn basically the entire internet, but still, you would think a model with 130 billion parameters would, when it has counterparts that only have 6 or 7 billion parameters, you would think that it would overfit at some point. I mean, like the human brain has 86 billion neurons, each with, I believe, between 2 and 12,000 synapses, making for just trillions and trillions of parameters. Yet, and while humans certainly do overfit on tasks, I would say that we are fairly well generalized to the world around us. So it's possible that certain models are able to either potentially not use excess parameters or find ways to just in one form or another mitigate the effect of what typically happens in classical models when you are over parameterized. So just something good to know about, but this certainly holds true for classical models. And I would say for more simple neural nets, this probably also may still hold true. I think the jury is potentially still out on that one. So let's talk about some different classification evaluation metrics. So what we're going to be talking about here are three different metrics. It's accuracy, precision, and recall. First, I'm going to just kind of like layman explain what these three different things are. So accuracy is how often you are correct overall. Precision is how often you are correct for how like often you are predicting for a particular class. Whereas a recall is how often you are correct for the target class. So let's do recall first because I think it's the one that is like the most clear. Um, so recall is the amount of times that you are predicting for how often you correctly predicted a particular class divided by the number of times that you were correct, plus the number of correct, plus the number of those classes, like, and how, so plus how often you were wrong for that particular class as well. So I find the easiest example to remember recall is heart disease. So if you're predicting heart disease, you want 100% recall. And the reason you want 100% recall is because you don't want people to die. Um, so you want 100, if you're predicting heart disease for the heart, whether or not someone has heart disease, you want, of all the times someone does heart disease, you want to predict that they have heart disease. So you can adjust the thresholds of your model such that this is true, but you will sacrifice being wrong more overall. So you'll predict more people have heart disease, but through that process, anyone who has heart disease, you have correctly predicted. So that's recall. Precision is of how often you are predicting a particular class. How often are you correct? So it's the number of true positives, so that you predicted a particular class and you were right about that particular class, divided by the same number plus how often you were wrong about predicting the particular class. So it's just like, how of a particular class, how often, of how many times you predict a particular class, how often are you correct that it is that particular class. And then finally, accuracy is just overall how often are you correct. So It's you predict the positive class and you predict the negative class, um, divided by, so how often you're correct divided by total number of predictions, is basically what accuracy is. So as a review, accuracy is how often you're correct divided by total number of predictions. Precision is for a particular class, how many times you predicted that class divided by how many times you predicted for that class. Sorry, let me rephrase that. How often you were correct for that class of those that you predicted versus divided by how often you predicted that class. And recall is how often you predicted target class out of how many possible target classes were there that, like, in actuality. So let's talk about kind of when you might use different kinds of classification metrics. And while doing that, we're going to talk about balanced and unbalanced data sets. So a balanced data set might be, say, you're trying to predict gender. There might be some moral qualms with doing that, but it's a good example for the sake of example. Um, so predicting gender, you expect approximately a 50-50 split. Here we have 50.4 and 49.6. So I think this must be a younger demographic because on average, I believe there's more women on average than there are men because men die sooner because they do stupid things. But it would be a bad idea to use. Sorry, we'll talk about this example before I move on to the next. Accuracy would be a fine metric to use here because our data set is balanced. Whereas if we have an unbalanced data set, accuracy would be a bad metric to use. And the reason that is because, like, if we were to predict, so in the case of fraudulent versus normal activity, if we were to predict normal, we would be right 99% of the time, which isn't really a great look into how our model is performing. Because what we're interested in is in the fraudulent class. So a metric that we'd probably more so would want to investigate is precision or recall. So especially for the sake of fraudulent activity, I'm probably more interested in recall, but if there's a high cost to being wrong about fraudulent activity, you'd want to use precision. Whereas using accuracy on a more balanced data set, accuracy is fine, because you don't really have that problem. If I just predicted male all the time, I would be only marginally more correct than female in this particular data set. So when to use precision versus recall? I kind of alluded to it on the last slide. Basically, precision, you want to use precision when the cost of making a wrong prediction for a target class is high. So the examples in this particular graph or particular figure, I'm not sure I fully agree with, if I'm being honest with you. Movie recommendation, food recommendation. Um, movie, you recommend the wrong movie, it's not the end of the world. Or food recommendation, again, I recommend a hot dog. Someone doesn't like a hot dog, it's not the end of the world. Might have a higher impact on money. A better example here would be something where giving somebody a faulty diagnosis has a high cost in real life, or per se you're trying to predict crime and you're trying to predict whether or not someone has committed a criminal act. Right? There's a very high cost to being wrong in that situation, for example. Whereas recall, the cost of being wrong is low, or at least significantly less than missing the target class. So earlier we used the example of heart disease. There's a significantly higher cost to being wrong about missing someone who has heart disease than predicting someone who does. You give someone a bit of a worry that they have heart disease, but ultimately they're still fine. Versus, we miss someone who has heart disease and they are now dead. So here they're giving an example of fraud detection and customer churn prediction. Again, I'm not sure I love these examples. Fraud detection can very much have a high cost depending on the actions that come after that. And customer churn, yeah, no, that's probably true. You want to make sure that you capture all the customers that churn and enact actions which are likely positive anyways to make sure your customer sticks around. So finally, regression evaluation metrics. Here we have two. There's more beyond this as well, but these are probably the two more common ones that work um, regardless of the model they're using to regress. So the first is MSE, or mean squared error, and what that is doing is you're taking um, the what you predicted minus the true value squared, and then you divide by the number of points to get the mean squared error. And the reason we square it is because depending on whether or not your value is larger or smaller than the value, then it could be negative, which if you sum that out, that leads to funny things. So mathematically, it's a little bit easier just to square it. Um, but then you can also have the mean average error, which instead of squaring it, takes the absolute value of the difference and then takes the mean absolute error. I think I said average. I mean absolute error just takes the absolute value and then averages it. And this, both of these will be in like rough units of distance from the data points. One is squared, one isn't. I think I find the mean absolute error a little bit more interpretable, but they each have kind of serve their purposes depending on the situation. Um, we can go more over this in the linear regression example. So this concludes the intro to machine learning. These are kind of like, hope these fundamentals help you in understanding some other models as we present them down.